In this lesson, we will be discussing projectile motion. In a previous class, we looked at motion generally with a focus on the equation of motion. So today, we want to take it a step further by considering a special type of motion known as projectile motion. A projectile motion is the motion of a body that follows a parabolic path. By parabolic path, I mean in a layman's language, a curved. So if something describes this type of a curve when it is moving, maybe something like this, that is an object that moves up and then get to a certain height and then comes back to the ground. If the motion traces this type of path as a PATH, then the motion of such object is described as projectile motion. That is, whenever an object moves in a curved path, in a parabolic path, then it is describing a projectile motion. For example, if you throw something like a tennis ball against a wall, when the ball bounces off the wall, you normally follow this type of pattern, a curved path. That type of motion is a projectile motion. This is the wall. Then somebody threw a tennis ball or anything that can bounce off the wall. Usually when it bounces off, it traces a curved path before landing on the floor. So such a motion is a projectile motion. Also, when you release a stone from a catapult, usually the stone traces this type of pattern. It goes to a certain height and then begins to fall down to the ground. The same thing if you throw a shot put or a javelin, when it goes up, it flies and follow this type of pattern, tracing a curved path before coming down to the floor. So all of these objects I just gave as examples, follow a path, a parabolic path, a curved path. Such motion are called projectile motion. So some common examples are the motion of a thrown rubber ball bouncing from a wall. Any elastic material that can bounces off a wall when you throw it against the wall, as it is coming back, as it is bouncing off the wall, it traces a curve. An athlete doing a high jump, when you jump in a high jump, you follow a curved path. If you are to trace your path, this is the barrier that you want to jump across. Normally go to a far distance and then run. When you are close to that barrier, you lift yourself against the barrier. As you are going up and coming down, you trace a curve. Then a bullet fired from a gun also follows a parabolic path. When a bullet is fired off a gun, it goes to a certain height and then comes to the ground. As it goes, it traces a curve. So all of that are examples of projectile motion. Now, there are two cases of projectile motion. We will look at a simple case, that is for an object falling from a certain height, and then a more general case for an object that starts from the ground, move all the way to the highest point, then come down to the ground. So there are two stages here now. When going up, that is a stage, and when coming down from the highest point, that is also a stage. That is a more general case of a projectile motion. But before we look at this, let's look at a simple case of a projectile motion. That is for an object that is falling from a height. Now, if this is a platform, and on this platform, somebody is standing on that platform, and then the person kick a ball or any object with an initial velocity. We kick the ball in a horizontal manner with an initial velocity, a certain amount of initial velocity, let's call it u. Now, as that object falls from this height, it's going to trace a curved path until it lands on the floor. Now, it's tracing this curved path because of the initial velocity of projection. Now, because of that initial velocity of projection, had it been there is no initial velocity of projection, let's assume this guy just dropped the object from a height without projecting it horizontally, then that thing will likely land on the foot of this platform. As in the guy is standing here like this, and then holding a ball in his hand, then he just release the ball. There is no velocity of projection, I just release it. Likely the ball will travel in a straight pattern and then land on the foot of this platform where he's standing. On the other hand, if the guy projects the ball with an initial velocity, the ball will trace a curve like this. So this is the guy standing here, and then this is the ball. The guy kicked the ball with an initial velocity u. Because of that initial velocity of projection, as the ball is traveling down the ground, it's going to trace out a curved path. Now, as it moves, there are two components of this velocity. The horizontal component, which is as a result of the velocity of projection, and the vertical component, which is as a result of the acceleration due to gravity acting on that ball. From our previous lesson where we discussed motion under gravity, we said when something is going up or falling down, there is a special acceleration that that object is traveling with, and that acceleration is the acceleration due to gravity. So this object, this ball in this case, is projected with initial velocity u. So as it comes down to the floor in this parabolic manner, there are two components of this velocity. The horizontal component is as a result of the initial velocity of projection. Then the vertical component is as a result of the acceleration due to gravity. Now, as it goes along, there is no extra force acting on it horizontally, but there is a force that is acting on it vertically, which is the force of gravity. So because there is no extra force horizontally, the velocity along the horizontal axis, that is the horizontal component of the velocity, remain constant. Remain what? Constant. That is, it does not change. On the other hand, the horizontal component of the vertical component rather, of the velocity increases by a value of 9.8 meter in every second. That is 9.8 meter per second. Why is it 9.8 meter per second, you may ask? Because the value of acceleration due to gravity is 9.8 meter per second square. So as this thing travels down to the ground, the two components of the velocity, the horizontal remain unchanged, the vertical increases by a value of 9.8 meter per second in every second. So that is what this diagram is trying to show us here. You can see in this diagram, we have two components of the velocity, the horizontal, which is as a result of the initial velocity of projection. You can see it there is u all through. Then the line, this arrow, they are equal. It is drawn in a way that the arrows are equal. The arrow is drawn to represent the magnitude of the velocity along the horizontal axis. The vertical line, on the other hand, the vertical arrows are increasing. They are increasing. They show that as this ball is falling to the ground, the velocity along the vertical axis is increasing for every second that this object travels. Now we can use an animation to illustrate that further, and I already prepared the animation here. Look at this. We want to release a cannon, and that cannon will travel with initial velocity of 15 meters per second. So because it's being released from a height, of course, there are two components of the velocity. The horizontal component, which is as a result of this velocity of projection, and then the vertical component, which is as a result of acceleration due to gravity. Now watch carefully what is going to happen. You will see two arrows, one in a horizontal axis, the other on the vertical axis. We take note of the sizes of those arrows. So let's go. You see what is happening? The horizontal arrow remains constant, the same length all through, but the vertical arrow is increasing as the object gets closer and closer to the ground. That is to tell us that the horizontal component of the velocity does not change because there is no extra force acting along the horizontal axis as this object is traveling to the ground. However, there is a force acting along the vertical axis, which is a force of gravity. So that force of gravity that is pulling the object down makes the object to travel faster as it gets closer and closer to the ground. So the velocity is increasing with a value of 9.8 for every 1 second as it travels down. So that is an illustration to show that when something travels from a height down in a parabolic path, there are two components of the velocity, the vertical and the horizontal. The vertical is increasing, the horizontal remains the same because there is no extra force acting along the horizontal axis. The vertical axis, there is gravity. So that is a perfect example of projectile. In this case, this is a simple case of projectile. It is falling from a height to the ground. Okay, so let's go back to the board. So as a stone is subjected to two independent motion, namely the horizontal motion and the vertical motion. The horizontal motion is independent of gravity. Therefore, it will remain unchanged until the stone hits the ground. When the stone is initially thrown forward, it has no vertical velocity. Look at it. Let's go back to that animation. There's no vertical. Watch it when the stone is coming out of the cannonball. And when the cannonball rather is coming out of the cannon, you see that there's no vertical arrow. Now see, watch it when it's here. The arrow is, did you see it? Look at this thing that looks like plus. When the cannonball is there, there's no vertical arrow. Because when it is there, it only has the velocity of projection, in this case 15 meters per second. So when the stone is initially thrown forward, it has no vertical velocity. But the vertical pull of gravity, we accelerate it downward at a rate of 9.8 meters per second squared. The vertical or y component of the velocity will thus increase by 9.8 meters per second for every 1 second. Is the force of gravity that brought about this vertical component of the velocity. So from the above, we can conclude that any projectile in flight is doing two things at once. Number one is flying horizontally at a constant speed, and number two, it is moving up or down with an acceleration g. Now the object is moving down. If the object is moving down, the acceleration will increase by a value of 9.8 meter per second for every second. On the other hand, if it is going up, then the body, the acceleration will decrease by a value of 9.8. Now, before something can move up, that means there must be an initial velocity of projection from the ground level. So if I project it, for example, with a value of say 25 meters per second from the ground level, as that thing is moving up, the velocity will be decreasing gradually. Why is it decreasing? Because it's going against gravity. The gravity is pulling it down. Why it goes, so as it is going up, the velocity will be decreasing until it gets to zero at maximum height, and then it begins to fall down, begins to fall down. So as it is going up, there are two components of velocity. Also, the vertical component, which is going up. In this case, it is decreasing because it's going against the gravity. The horizontal component, which is constant, because there is no external force acting along the horizontal axis. So as this thing gets to the highest point, the vertical velocity becomes zero, and then it begins to fall down. As it is falling, the horizontal velocity still remains constant, but the vertical velocity will be increasing. While coming down, while going up, it is decreasing. While coming down, it is increasing. So I also prepare another animation for that. Let's go and watch it. My animation is somewhere here. Yeah, here it is. So watch what is going to happen in this thing. This is the object in this case, and we want to project it with initial velocity of 25 meters per second from the ground level. As it is going up, there are two components of the velocity. The vertical component, which is going against gravity in this case when it is going up, the horizontal component. Now the vertical component will decrease when it is going up, the horizontal component will remain constant. So watch what is going to happen in the arrow until we get to the highest point. you will see that the vertical arrow will be decreasing while the horizontal arrow will remain constant. You see, you see. Then when we get to the highest point, the vertical arrow becomes 0, while the horizontal arrow still remains the same length. Then the moment the vertical arrow becomes 0, that thing begins to turn back and then come back to the floor. As it comes back to the floor, the vertical arrow begins to increase. So let's reset and repeat it again. Watch it clearly. And if it, when it gets to the highest point, the vertical arrow becomes 0. Then it turns and comes to the floor. Let me repeat it for the last time. Then watch it when it's coming down now. You see that the vertical arrow is growing as it is coming down. That is to tell us that, okay, when an object is going up, the vertical velocity will be decreasing because of the effect of gravity. That object is going against gravity. As such, the gravity is pulling it down. That is what is decreasing the vertical velocity. The horizontal arrow remains constant because there is no external force that is acting along the horizontal axis. Then when you get to the highest point, the vertical arrow becomes 0 because that thing is going up because of the initial velocity of projection. And gravity is reducing that velocity. It reduces it until it becomes 0. And then when it becomes 0, there's nothing that is pushing that object up anymore. So the object turns and then begins to come to the floor. And as it comes down to the ground, the vertical component of the velocity will increase because of gravity. Gravity is pulling it down, and so the vertical velocity will increase. The horizontal velocity remains the same because nothing is acting on it along the horizontal axis. Okay, so those are the two cases of projectile, the simple case and the general case. The simple case has to do with an object that is thrown horizontally from a height, that is with initial velocity of projection. It traces a parabolic path as it comes down to the ground. Two components of velocity, the horizontal component, the vertical component. The vertical is increasing as it comes to the floor, that's increasing by a value of 9 point. The horizontal remains the same.